All right, next topic is flux integrals. This is also known as surface integrals in vector fields. So these are calculated as the double integral over a surface of the vector field function dotted with n, and n is the normal to the surface ds. So to say some things about this s, which is a small s, don't get confused thinking that this small ds means the arc length differential. This is a different small s. So think about it like this. You have to have two vectors to take a dot product. Essentially what a flux integral is, which maybe I should have led with, is just the vector field f dotted with d big S, which somehow includes a vector portion. And I don't fully understand how, but it does. So when we change to this more practical and useful formula with the n, well, n is a vector, obviously, so we just fulfilled this two vector requirement. So we change d big S to d small s, because the small s does not have any vector representation, because we don't need three vectors in there. Okay, so both of the formulas I just talked about for flux integrals were actually just conceptual. So here's the actual practical formula for computing the flux integral. And note that it requires doing the same thing as with a scalar field integral, where we get a function g in terms of two other variables. So that being said, it is the double integral over region D of negative p times g sub x minus q times g sub y plus r dA. So to just talk about the letter D, the D is the letter R, same as we use in the scalar field integral formula. We're just changing the letter so it doesn't get confused with the R that's in this formula, which is, like the k hat component, since we're in the three dimensions now. And on that note, as a reminder, the letters P, Q, and R are just the components.